Hi everyone, so today let's talk about MO of simple linear molecules. Very simple, very easy. So we're gonna use no character tables today because we need to do lots of stuff with character tables. If we actually need to use character tables, we need to find irreps and find the interactions between or whatever. It's a mess. So let's see for simple linear molecules. For example, the first one we have the linear trihydrogen cation, which is in its linear form. There's also its cyclic form, but let's consider the linear form today. So what we're going to do is we have to draw out what the trihydrogen cation looks like. So you will see that there's these two hydrogens, which are bonded to this central hydrogen. And what we're going to do next is we're going to divide it into two groups. So the first one is the central atom. We're gonna consider the central atom, and then we're gonna consider the ligands. Now the ligands are just the atoms that are bonded to the central atom. We just call it ligands. So after we divide it into a central atom, in this case it is a proton, because this hydrogen is a proton, and its ligands, it's just going to be the hydrogens that are bonded to the central atom, and this dot means it's just a place for the central atom. Now, for the central atom, what we're going to do next is we're going to consider which orbitals the central atom can use and which orbital groups are there for the ligands to interact with the central atom. So for the central atom, there's only one s, right? Hydrogen only has its one s orbital. So this is its one s. Let's draw it in phase, which if we imply a symmetry operation of inversion, the phase of the orbital will still be the same, right? For 1s, we invert it to a center of inversion, it's gonna still be a plus phase. So let's call this a Gerada 1s. Gerada is just a fancy way of saying, oh, when you use an inversion symmetry operation, it still retains the same phase. Now let's look for the ligands. The ligands are no different. We just have one s that are in phase of each other, right? And you also have another group that is not in phase of each other. So it's going to look like this. And the same thing is if we apply a symmetry operation like inversion in this case, you're still going to get that, this, when you invert it through the center, it's going to still be a Gerada. And for the right one, now if you use the inversion operation, this plus phase will end up on the right side instead. So this one is an ungerada, because when you use the symmetry operation of inversion, it now has an opposite sign. So there's the ungerada. Now, an easy way to tell which orbital interact is that same symmetries interact. So as you can see, the Gerada and the Gerada will just interact, or you can just draw it out, like which symmetry interacts. Let's say I didn't use the Gerada or ungerada name for each orbitals. I can just still say that, this orbital interacts beautifully, right? This one right here, because it's in phase of each other. In fact, it is, and then this one is the bonding type interaction, right? And for the anti-bonding, I just make the 1s of the central atom, out of phase of the two ligand groups, the ligand group orbital, right? And in fact, I'm gonna give it a name too for these two interactions that I've just drawn it out, and I'm just gonna still use the inversion operation. So invert it through the center. I'm still gonna get this one is a Gerada, and this one, I cannot use that anymore because, or maybe I can say that this is a Gerada star, right? Because this is anti-bonding, so I'm just gonna say it's a Gerada star. Or you can give it other names too if you want. I don't know, something like a different name, I don't know, but I'm just gonna use Gerada. I'm just going to use the symmetry operation to differentiate the two orbitals. And for the Ungerade, so let's consider the Ungerade group orbital. Does it have any interactions really? No, right? Because the phases cancel out. So the Ungerade group orbital is non-bonding. So we have only two interactions. And so now we can draw its MO. So we're gonna put normally we put the central atom on the left, so we're gonna do that. So the central atom is the proton, and the group orbitals, which is the ligands. Great. Now these orbitals are both 1s's of the same element, so I can expect for the the energy level to be the same. So yeah, these energy levels are the same because they're both 1s's of the same element. So then we're gonna label the proton, this one right here, it's gonna be the 1s of the proton. And for the ligand group orbital, this one of them will be a Gerade. Let's use a capital G then, to not confuse which G is which. And this one will be a capital U. Let's use a capital G and a capital U. Great. Then let's fill in its electrons. Oh wait, let's draw the interactions first, then we fill in the electrons. And there's gonna be two interactions, right? As I said, there's gonna be a G and a G star. So there's gonna be a G and a G star, right? And there's gonna be one non-bonding, which is the U. One non-bonding. So this one will be non-bonding. Great. Let's fill in the electrons. We're gonna get that the hydrogens here have one electron each, so there's gonna be two of them. And this one will be a Gerade star. This one will be a U. Oh, capital U also, because well, I've labeled it as U. It's non-bonding. But normally in the MO diagram, we usually use small letters. So let's use small u. So let's fill in the electrons. And that's it. That's it for the trihydrogen cation. And in fact, this orbital is bonding. This is non-bonding. This is anti-bonding. Anti-bonding. So the bonding will correspond to the first interaction here, right? G is just here, and the G star is just the one with the orbitals out of phase of each other. And so what does this tell me? This tells me that the bonding MO has 3 atoms, right? 2 electrons. So this is a 3 center 2 electron bond, similar to the one you see in diboring, right? The B2H6, with hydrogen acting as the bridge, right? So it's a 3 center 2 electron bond. And that's how you draw an MO for the trihydrogen cation. Let's move on to something more complicated, like this anion. This anion is linear, and the shape of this anion looks like this, with the hydrogen in the middle carrying the negative charge. So we're going to do the same thing, is that we're going to split into the central atom. In this case is the hydride. So what orbitals do we have in the hydride? Still only 1s. And the ligands. Now we have the fluorines. And what orbitals does fluorine have? We have the 1s of the fluorine, right? We have the 1s of the fluorine. 1s of fluorine. We also need to draw its out of phase version. Fluorine 1s's. There's also the 2s's of fluorine. 2s's of fluorine. And then you have the p's, right? The p orbitals. So I will also need to assign the axes. So let's say that this is the z-axis, the bond axis is z-axis, and this will be the x and y. So this will be the py. I'm just gonna copy. So this will be a 2py, and this one will be in phase, this one will be out of phase. Then we're gonna also have the px, the 2px's, 2px's, we're also gonna have the pz's. These are the pz's. Forgot to draw the phases. Two pz. Great. Thing here is 1s of fluorine is just, it doesn't interact anymore. Fluorine, we're not going to consider the orbitals that is not part of the valence electrons. So we can just delete 1s out of the way. We're just going to consider only the orbitals that contain the valence electrons. So we have 2s, 2py, 2px, and 2pz, right? These are the orbitals that contain the valence electrons and the 1s of the central atom. What we're going to do next is we're going to also see which orbitals, which orbitals interact in terms of energy, because the 2s of fluorine and the 2py, 2px, and 2pz of fluorine are in different energy levels. So then we need to consider which orbital interacts in terms of energy. And for the orbitals to interact efficiently, the energy difference of the orbitals must not exceed around 13 electron volts, let's say. But there are some cases that, maybe 14 electron volts, they can still interact. But, this is a general rule of thumb, let's say. And so let's see which orbital interacts. So right here, the hydrogen 1s orbital and the fluorine 2s orbital, it's so high in energy difference. It's around 27 electron volts. It's so high, it's not going to interact. 27 electron volts is massive. It's twice the threshold, right? But the 13 and 18, that's 5 electron volts that can interact easily, right? So the 1s and the 2p, the 1s of the hydride and the 2p of the fluorine will interact, of course, and the 1s of the hydrogen and the 2s of the fluorine won't interact. It's way too different in energy. So we're going to list that. So we're gonna say that 1s of central atom interacts with 2p of ligands. Next, we're going to consider which orbitals interact. So first, out of the bat, you can see that this orbital interacts, right? Here you go, and it's non-bonding. And also it's non-bonding partner right here. So let's see what else interacts. 1s of central and 2p of ligands. And actually that would be it. There's only one pair of interactions here. It is the pz and the s orbital of the hydrogen, and that's it. And all the other orbital groups are non-bonding, all of them. So yeah, we can now draw the what do you call this, the MO diagram of fluorine and hydrogen. So to start, we're going to put the hydride on the left side as usual. That's going to be the hydride 1s, right? And then we're going to have the ligand group orbitals of the fluorine. Fluorines. And let's split these into two groups of degeneracy. By degeneracy, I mean equivalence in energy, because because the orbital energies of 2s and 2p, of course they're not going to be the same, right? 2p in this case is obviously higher in energy of the 2s orbital of the fluorine. So 2s and 2p, they're going to be different in energy. So yeah, and the 2s of fluorine is going to be so here. It's going to be so low because, oh well, it's what you call this, it's negative 40 electron volts in energy, as you can see right here. So it's going to be so low in energy. So it's going to be so low right here. Yeah, and then you have the 2p's of the fluorine, and it's a bit lower in energy than a 1s of the hydride. So it's going to be maybe here. And there are going to be 6 of these because, oh well, you have 6 ligand groups orbitals. Great. So let's start building the MO diagram. So the 2s's will be non-bonding. Non-bonding. Let's give it a name too, shall we? Let's give these some names. Let's call this Bob and Bob and Bob. Let's call this Bob Garada and Bob Ungarada. Wait, I'm just gonna use it as a subscript. Bob Garada and Bob Ungarada. So that's gonna be Bob Garada, Bob Ungarada. Great. And then the 2p's is gonna be interaction between 1s and the 2p's, right? And the orbitals are very weird in its shape. Maybe it's not centered well. So let's move this one a bit closer. Yeah, I'm very quite neat when it comes to these things, I guess. Oh well, whatever. Okay, 1s and the 2p. So it's going to be these two of these. Well, let's not call it Bob anymore. This one yeah, whatever. I wrote Bob down here, but let's not call it Bob anymore. Let's call it Adam. This will be Adam star. I mean, you can really name your orbitals anything, but just don't name it Bob or Adam. It doesn't really communicate anything, but for the sake of video, I'm just gonna name it Bob and Adam. And the non-bondings, of the 2p. How many are how many of these are there? How many non-bondings are there? Or the 2p's? There are 1, 2, 3, 4, 5, 6, 7. So there should be 5 non-bondings up here. So 5 of these so there will be gonna be 5 non-bonding MOs. I should use a dotted line. That's even more confusing. Let's use a pointed line. Yeah, okay, that's better. Okay, good. I should also turn these into pointed lines so that it wouldn't confuse with the MO itself. Great. Okay, this looks good. Let's call the non-bondings. What should we call them? Let's call it a family. A family of non-bondings. Family of non-bondings. P orbital. Non-bonding 2p. There you go. All right. Bob and Adam. So now we have Bob G and Bob U and Adam star. So what we're going to do next is we're going to fill in the electrons. So fluorine, how many valence electrons does fluorine have? 14, right? I mean, 2 fluorines have 14 valence electrons. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, great. Let's fill in. So these will be not bonding. And how many electrons do we have here in total? 1, 2, and how many of these? 10, right? It's 12 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You shouldn't do that, but I'm going to do that anyways. You should fill the electrons from left to right, but I mean, it's all degenerate. So, yeah, so here's the MO of the molecule we're considering. Negative charge. Here we go. Great. And thank you for watching my video.